All right, everyone. So today we're going to talk about Google Dataflow, which is one open model for batch and stream processing. Just a quick show of hands. How many of you have used Dataflow before? All right, looks like not that many of you, so hopefully you'll learn something new about it today. First, a bit about us. My name is Sara Robinson. I'm a developer advocate on the Google Cloud Platform team. I'm based in New York. Super excited to be here in Antwerp today, first time here. You can find me on Twitter at srobtweets, and my GitHub is SaraRob.
Hi everyone, I'm Robert Kubis, also a developer advocate based out of London. You can find me as well on Twitter, and I always mention what is an advocate. We are basically your megaphone into the Google organization that build the products for you. So if you have challenges with using our products or you like our products, we also like to hear that. You can find us on Twitter and just tweet us, and we try our best to make the products better. All right, so today we're going to talk about Dataflow and the road to Dataflow. So we're going to start with a little bit of history. So we want to frame the whole discussion, like how did we get to Dataflow and what is it all about? So Sara is going to talk a little bit of the big data history.
Thanks, Robert. So we have a timeline here, and I'm going to start with MapReduce, which was a paper that was published by Google in 2004. And the big change with MapReduce is that instead of running a job on one computer to process data, you could distribute the job and run it on many machines in parallel. And this is what a typical MapReduce batch processing pipeline looked like. So you have a lot of elements as input, and then you divide them into chunks, and you divide these chunks among many different machines, and you run a map function on them. So this is going to be an element-wise transformation that you run on each element. And then from these mapping machines, you distribute them to a series of reducing machines where you'll do some sort of aggregation function. So maybe you'll group all the elements by key. And that's what you'll do in the reducing phase. And then you'll produce your final output. So engineers at Google started using MapReduce for any sort of big data job. And it was great, but it was fairly limited. It was a single select followed by a single group by. And people at Google kept reinventing systems to chain multiple MapReduce operations together, and thought maybe there could be a better way. And the next paper that I'm going to talk about is Flume Java. Flume Java was published in 2010. And essentially what Flume Java was is a higher level API built on top of MapReduce. So with Flume Java, developers could focus on the algorithms and not the underlying systems to run their pipelines. So the system would automatically transform their job into a series of MapReduces, and there was some higher level, easy to use functions to build their pipeline. And this is some Flume Java code that I'm going to walk you through. It's actually pseudocode, because if we wrote it all out, it would be a bit longer, wouldn't fit on the slide. This looks very similar to the current Dataflow API, which you'll see a little later on in our presentation. So in this example, we're computing the mean temperature. So let's say we have a lot of IoT sensors all over the world in different locations, and they're emitting data on the temperature in whatever location they're in. So we start with a series of raw events, and Flume Java introduces the concept of a P collection, which is essentially just a collection of data that we want to process. So we have this raw collection of events, and then in the first phase of our pipeline, we're going to transform each event into a more structured key-value location temperature pair. And we can do that using a par_do, which is a parallel do function. So this will perform this function on each element in our P collection. And then we want to do an aggregation function. So we want to find the mean temperature per location to change our P collection into this key value pairs, and then we'll write that output somewhere. So this is a quick intro to what the Flume Java API looks like. So many people started using Flume Java to process their data. It worked really well. Lots and lots of data, even more data. And a common thing to do is if you have constant data coming in is to divide it into chunks, maybe chunks by day. So let's say we have a lot of log files. Typical way to process them in this situation would be to periodically write a job that processes all the data from the beginning of time, or we could process it in chunks. So we could process all the data from Tuesday, Wednesday, and Thursday independently. So it seems like we're done, right? We have a solution, a batch solution where we can process all our data from the beginning of time, but we can also divide it into chunks. But there's actually a couple problems with this solution. So if we're processing the data in chunks, like by day, Let's say we have a pipeline that does some sort of abuse detection, where low latency is really important. We need to do something right when we detect abuse in our system. Well, the thing I mentioned before won't work in this situation, because if we're waiting till the end of the day, the end of the hour, to process all of our data, we'll miss those abuse situations. Another way this won't work is if we're dealing with user sessions, so bursts in user activity, and we still process our data in daily chunks. You can see in this example, 2 of our users, their sessions were split into 2 chunks because they were between 2 days in the data we were processing. And often today, we're dealing with continuous and unbounded data. So we don't have a finite set of data. It's always coming in. And it has unknown delays, like network delays. So here we can see a bunch of elements that we're processing. Here, the red element occurred at 8 a.m., and it was processed just slightly after 8 a.m. So just maybe a small network delay. We can see the yellow element occurred at 8 also, but it was processed about 30 minutes later, maybe a little more of a network delay. But then we can see this green element over here, which there was a delay of a couple of hours. Maybe the user was offline. Maybe they were climbing a mountain. So it took many hours to process this data. So we need a way to deal with this situation. I'm going to hand it over to Robert to talk about how we deal with unbounded data.
Yeah, so we needed a system basically that can work on this unbounded data, on a stream of data, to give us like more fresh results, more real-time results. So you can imagine like Google became great or big through search, right? And search is also about freshness of data. So if you search for a game, for instance, a soccer game, how Belgium plays against France or something like that, you want to have basically an accurate score at that moment in time. So what we developed within Google is a system called Milvia, and we published this paper in 2013 to like talk about like how we deal with that. So basically, what is Milvia about? It's basically a framework where you build a directed acyclic graph, which does an element-wise processing on your elements that come on the stream. And then the system manages for you the persistent states and like the movement of data between certain graph nodes. So if you look at it, like it's pretty much like what you do in a Hadoop like manner. Like you want to extract the key from your elements and then group them and whatnot. So basically, instead of doing that on a batch of data, you do that basically on every element that comes in. So you have element-wise transformations. So extracting a key, grouping, then doing the grouping, and then doing the aggregation. But you still like have the challenge, like you want to calculate some results in terms of you want to do some aggregation. So we are still at the point that we do need to bound this data into so-called windows. So we see here, like again, we have these windows where we group this data in. But most of the streaming systems, if you look at them today, what they do is basically they window the data by the time it arrives in your system. And that, as we have seen, and as Sara has explained, data can be delayed. What means basically if you window the data by the time it arrives in your system, you could get incorrect results because it doesn't actually reflect when when the event happened. So another thing is so what we need basically to do is we need to window these things by the time when these events actually happened. So we distinguish between event time and processing time. So event time, when the user crashed the candy in his mobile game, and then processing time is when the element actually arrives in your system. But we need to know like how long do we keep these windows open and things like that. Also, do you have other mechanisms that we have seen before? We want to maybe window these not only by time, we also window them by user burst, with basically on a session basis. And even if we window them by the session basis, we need to know like when can we actually close these windows? When do we like know that all the data is there, or like when do we expect that all the data is there? So what we are actually adding there is like we formalize the event time versus processing time. And we basically, what you see here in the graph, you have on the y-axis processing time and on the x-axis an event time. The dashed line that you see there is basically our real-time line. Every element that happens in the lower right corner, please let us know. I want to know how you did that. That's basically if you time travel and you see an event in your system before it actually happened, it would end up in the lower right corner. So that would be pretty cool, but still even Google doesn't know how to do that. So you have this watermark, and the watermark is basically, I talked about how we need to close this window at some point. And we need a heuristic to know, like, okay, we believe that now all the elements till a certain amount, to a certain point in event time arrived in our system so that we can close the window. And so the watermark is basically the heuristic to have the estimation when we have all our data. The skew that you see there is basically the delay between when an event happened and the event when it comes in. All right, so there are a couple of scenarios where you have to think about, like, okay, what do I use? Do I use a batch system or do I use a stream system to tackle this big data problem? So I'm going to talk about a couple of these scenarios, and I want to use 3 criteria to talk about them. One is completeness, in terms of like how correct, like I want to have correct results or not. The other one is latency, basically when do I get the result from my data? Do I get it like in real time or do I have to wait? And the third one is cost, like how much do I have to actually invest to run these pipelines? So you see here a graph which shows you on the y-axis the importance of these 3 criteria, and on the x-axis basically the 3 criteria. Before I talk about this, like there's one challenge in this graph. We have in the middle the low latency graph, and it's kind of a little bit reverse thinking. If the low latency graph is low, it doesn't mean low latency, it means the low latency is not important. So I just want to point that out because it triggered me up a little bit in the beginning. All right, so first example is a billing pipeline. So in the billing pipeline, you want to be correct. So it's really important that we are complete in our calculations. You don't want to charge your customers a wrong amount, or you don't want to get back to them and saying like, hey, like I need a little bit more money from you from last month. So it's really, really important that this is complete. Latency is not that important in a way, like it can take a little bit longer after you close the month. It can take a day or 2 or even 3 till you charge your customer. It's really more important that it's correct. And then low cost, cost is not that important. Basically, you actually want to have correct results, so you want to spend some money to have actually correct results. The next element also in the billing scenario is a live cost estimator. And there it's like a little bit reverse. So basically in the live cost estimator, you don't need to be 100% correct. It's okay if you're a couple of cents or maybe €1 or so off, but you want to give your customer like kind of a runway, like where he's heading to in terms of cost to the end of the month. So low latency is important there. I mean, like if it's very delayed, then it doesn't give a real picture what this runway is at. So you really want to have this like really fresh. And low cost in terms of like, yeah, you want to run that like continuously, and you don't want to spend all your profit into running this pipeline. So you want to make sure that this is not too expensive. But you can basically make the trade-offs between correctness and cost here. Another scenario is abuse. So, like, assume like you have basically a system where you want to detect abuse, and training a model basically you can do that offline, but detecting abuse you want to do that in time. So again, here low latency is really important. The sooner you detect abuse, the better for you because you can avoid costs that you can't recover. Right? Completeness is not that important in terms of like you can do a mistake there. You shouldn't do too many mistakes, of course. You shouldn't throw out too many of your good customers. But still, like there are some ways to reconcile. And low cost is here not important. Again, like you can spend some money on this pipeline in a way. If you detect abuse early on, you can save money by detecting abuse, so you can spend some money into that pipeline. But for actually training, like usually what you use is like you can use machine learning to train your abuse models, and you can do that offline in a batch processing. There, low latency is not that important. You run that maybe once a day or maybe once a week. You want to have low cost if you run it like even more times, and completeness here is somewhat in the middle of importance. All right, so like if you look at these 4 scenarios, they covered both streaming and batch scenarios. And if you look at traditional systems, how these scenarios were solved, basically what you've done is usually a lambda architecture, where you have one system which does your batch processing, and you have one system which does your stream processing. And the caveat here is basically you have one system for batch processing, which means you have to maintain the infrastructure, you have to have experts for your batch processing, all that. And then you have one system for stream processing, which means you have an infrastructure for your stream processing, and you need experts in your stream processing. So Dataflow addresses exactly this challenge. We wanted to have a system where you can do both in one system with one program model within one infrastructure. And Sara is going to talk a bit about Dataflow.
Thanks, Robert. So as Robert mentioned, Dataflow gives us the best of both worlds. So we get the powerful batch processing from MapReduce, we get the easy-to-use API from Flume Java, and then we get the stream processing from Milvia. And to talk about Dataflow to you, we've built a demo application, which you'll get to try out at the end of the presentation. It's a super fun mobile game, and this is an overview of how it works. So it's a game where you see a bunch of different colors flashing on the screen. You'll be assigned a team, and your goal is just to click on that color and follow it around the screen. So we're capturing all the click events to see if you selected the right color, if it was a hit or a miss, and then we're summing up points per team. So to do that, we send each click event to PubSub, which is essentially a messaging queue, and then we send that to Dataflow, where we have a pipeline, and then we send the data back to PubSub. And then on our client, we're using WebSockets to listen for whenever there's an updated team score or player score so that we can display that in the UI. And then additionally in our pipeline, we're writing all of our data to BigQuery, which is our big data analytics warehousing tool, which you'll see a bit more later on. So we're archiving all the raw events in BigQuery. So throughout each step, as I introduce Dataflow, I'm going to relate it back to the gaming example, and then you'll get to see it at the end. So with Dataflow, we have 4 main questions. The first is, what are you computing? So what type of transformations do you want to do on your data? And this is essentially the MapReduce step. The next thing we want to think about is where in event time we're calculating our results. And then finally, how does the time that the event arrives in our system affect the way we're calculating results? So when in processing time do we want to emit results for our pipeline? And then finally, if we're emitting multiple results in a certain window, we need to decide how we want to add up those results. So first we'll look at the what. The what are you computing? And there's a couple different types of transformations you could do on your data. So the first is the element-wise transformation, which is similar to the map function in MapReduce. So you're performing a transformation on each element, which you do using the parallel do function provided by Dataflow. Another type of transformation you could do is an aggregation function, so grouping by key or combining or counting. And then finally, we could have composite transformations, which is essentially chaining multiple transformations together to create some sort of custom transformation. So one example is you could do a parallel do followed by a count followed by another parallel do. So let's take a look at some sample code for our gaming app. So here we've got a collection of raw log lines that are just score events in our game. Someone's tapping a button in our game. And we start with a P collection of just raw log lines. So each line in this file is an event. And then we want to create a more structured P collection. So we want to turn these raw lines into key value pairs of a team and the score that that person got for that particular event. And we'll use parallel do to do that. And then finally, we want to do a composite transformation. So we want to aggregate all of this so that we can get the score per team for each window that we're calculating for. So here's a graph that, so throughout each step, I'm going to show you a different graph. So this is one team's scores in our game. And on the x-axis, we have event time. And the y-axis, we have processing time. So here we can see this dotted line is ideally, we process each event exactly at the same time that it occurs. But in the real world, this isn't actually what happens. So we have an event like the score of 3 right here, which occurred right before 1207 and was processed just shortly after 1207. So that was pretty good, not too much delay. But then we have something like the score of 9 here, which was processed at occurred at 1201 and was processed just about 7 minutes later. And now let's see here. So the white line is our system processing the events as they occur. And you can see that when it turns blue, that signifies that it's calculated all of the results. So here it's waiting for each event to be processed to emit the final results. We don't emit anything in between. And now I'm going to hand it over to Robert to show some code from our app.
All right, so we're going to build actually this app like that we talked about. This is the app. Basically, we ask everybody later to play it with us, but right now we want to have you concentrate on how we do the coding. So basically, this is the app. Like every time I click on any of these fields, an event is emitted and sent to PubSub and then to Dataflow. So let's build this pipeline. So what I have here is basically, in this scenario, I'm reading from my PubSub pipeline. So I hope this is visible. So this is my input, basically. This is my game event stream where all the events are happening. And then, as mentioned, we are archiving all this data. So this is always a good practice to archive the data. So the first thing that I want to do is actually, which you are very familiar with in terms of like if I do batch processing. What I want to do is, first thing, I want to extract a key. So I basically go onto my P collection. This here in the P collection is a type table row. So I have my stream, and the first thing that I want to do is I want to extract the keys. So I do of key, and then I do key by team. So key by team does nothing else than basically going into my stream. It's a JSON object that I get. Let me make that a little bigger. I basically get out like the team element, which has a string like red, green, yellow, or blue. All right, so now I have that basically keyed. So next thing what I want to do is I want to group it. Like map reduce, you're basically extracting key. Next thing you do a group by key. So I do the group by, and that basically groups my like by these 4 teams that we have. And the next thing that what I want to do is I want to do an aggregation. So here I want to do actually, and I want to do that in parallel, of course, for each of the groups. I want to do a calculation for my team stats. So let's have a look at the team stats. Like it's very straightforward. Basically what I'm doing is I'm extracting hits. Like hits is basically if you hit the right color, so you're team red and you hit the red color field, that gives you a score. And then we extract things like the device and the hit rate and things like that for the aggregation. So pretty straightforward. All right. So with that, basically, we have our batch processing. So this is basically if we have a bounded data set, we could execute that right now, and it would create us a result. All right.
So we're going to go back to the slides. So as Robert mentioned, that works if we have a bounded finite data set. But in our game, people are going to be playing all the time. So we need to tell our pipeline when we want to calculate results. Because if we just use batch processing, it's not going to work in that situation. So we're going to use windowing to divide our data into event time finite chunks. And there's a couple ways that we can window our data. The first is fixed windows, which is the most simple. That just says, give me the total results every 2 minutes, every hour, every day. Or we could use sliding windows. So we could say every hour, give me the results from the last 24 hours. So it's sliding as time goes on. And then finally, we could use session windowing. So we could window by bursts of user activity. And so here's what our code would look like if we added fixed 2-minute windows. And back to our graph, now we can see that we're calculating the results every 2 minutes for this team's gameplay. But we're still waiting for all the results to be processed to calculate the final result. And now we're going to switch back to the code.
All right, so basically what we have here is like what we can do with the windowing is you can see like a development of a score or throughout the day, for instance. But you still have to wait till the end of the day to get actually this development of the score. So we do the same, like what we decided in our demo, we want to do a windowing into fixed window. So what you do is basically you apply to that stream that we apply a window. And it's like, you can almost read it. It's window into, and then we say fixed windows, Um, and then we say off, and then a size. So this is the duration. We want to have minutes, and we say like, okay, let's do a 5-minute window. So basically, like we chunk our data in 5-minute windows. But now it's still like, yeah, we need still to like a couple more steps to get actually to stream processing. So what is the next step?
All right, so our next step is we need to think about when in processing time we're going to calculate results. And we do that with triggers, which will control when our results are emitted. And triggers are relative to the watermark. Remember, the watermark is that heuristic about event time progress. So it's our system's best guess that it's seen all the data for a given window. So here we're going to trigger at the watermark, which is actually the default, but we put it here just for clarity. So we're going to trigger just when the watermark reaches the end of the window. And let's take a look at two graphs of how this would work. So on the left side, we have the perfect watermark. In an ideal world, we hit the watermark just after we finish processing all of the data for a given window. But in reality, we have our heuristic watermark, which we see on the right-hand side. And there's two problems with our current model. So right now, you can see that the score of 9 is completely left out of our processing pipeline because it comes in way after the watermark has already passed. And then we can also see that in 2 of our windows, we have multiple results. So it might be good to emit speculative results so that we can see the results before we've hit the watermark.
All right, so how does it look in our code? Like, basically, we need to basically trigger the results once like the window, like the watermark passes our processing time. So what we actually do, we add a trigger to our window. So what we do here is we want to have an after watermark trigger past the end of the window, and then basically, so basically, like we do this, and because we have the different elements here, we need to actually cast this to table. Okay, so basically now we have like the triggering, but as Sara mentioned, this is basically like when it passes the watermark, it emits a result, but maybe we want to have some speculative results. Maybe what do we do about this late data? This boils down to correctness here. So what do we do with this?
So we're going to add some rules here to account for early firings. Remember I showed you in the graph before, we had 2 of our windows where there was a couple of results that came in before the watermark. So we're going to emit results every minute. And then we're also going to add this rule to account for late firings. And the one there just indicates that every time there's an element that comes after the watermark, we want to emit results for that window again. And so this brings up the question of, as we're emitting multiple results per window, how should we account for those results? So should we emit them as a running sum, or do we only care about the values that have come in since the last time we emitted the data? So in this example, we're going to add a rule to accumulate fired panes. So we're going to accumulate the total as we emit the results for a given window. And here's what it'll look like. Again, on the left side, we have the perfect watermark. And then on the right side, we have our heuristic watermark. So we can see that in this case, we did account for that 9 because we added that rule to emit results whenever there's late data that comes in after the watermark. And then you can see in our second and our fourth window, we're able to emit early firings every minute for every time so we get all those early elements that came before the watermark. So let's see what that looks like.
Yeah. All right, so basically we have our trigger as we saw before, and now we need to add like to enhance our trigger for early and for late data. So we add an early firings, and we say after the processing time. Basically, that is the time when in your window, like while the processing time advance, pass first element in pane. First element in pane is basically the first element that is windowed in one of your windows is the first element in that pane, and then we add a delay of a duration. So what I want to have here is I want to give results because we want to have like kind of a real-time demo here. We want to actually have a result emitted every 10 seconds. All right, so this is our early firing. Now we want to account also for late data, so we have to enhance our trigger for late firings as well. And here I do an after pane, basically, which basically means like after the window is closed, anything what happens after that. And what I want to do here is like whenever an element comes into our system late, like after the window was already closed, like every time I want to emit a new result. So I say like, okay, like even if one element only comes in our system, I want to emit a result. All right. So after that, we still have to say things like, okay, how much lateness do we actually allow? So because like the system has to basically keep the state of like what are the closed windows and what are the elements in there. So if you would just do infinity, you would run out of memory at some point. So what you want to do is like you want to set a boundary in terms of like how late of data do you allow actually. So in our case, I want to have, let's say, 10 minutes of late data that I can arrive. So now we have like accounted for late data. We know what we're going to do, like in terms of if we have early results, we emit them every 10 seconds. But there's still like missing here the fourth question. And the fourth question, basically, I have to define like what am I doing with the results that I'm emitting. So in my case, I want to accumulate. I want to always like add basically each new element that comes into my system. I want to add that to my aggregation. So having this is basically our pipeline. And I'm going to talk a little bit about the other things that we have here in our code. So once we have like basically what we do here is our windowing. So we window, we do early and late firings, and we do accumulated fires. We have seen we do our grouping and our keying for team stats. We also do that for player stats. I also want to know what is the hit rate for a player and things like that. And then last but not least, what we do is we write it out back to PubSub again, and also to BigQuery, just because we can, basically. And then like what Dataflow is all about, you build a graph here. And you don't like fill it with any kind of data. The data like comes in when you actually start and run this pipeline. So you have to, at the end, you have to actually trigger the run. Like now I want to run this pipeline. So I'm going to show how do you actually deploy this. So we have here, it's based on Java. I'm using the Java SDK. It's in version 1.8 right now. So I'm running this on the Google Cloud Platform Dataflow service. And you have basically to define the main class, and you have some job arguments. In this case, what we give a job name, we give the project that we are using, we give a staging location where like our code is staged in the cloud, and then we define a runner. So Dataflow supports a local runner or like the Dataflow runner. And then we also define that we want to have streaming. Since this is like a rather small room, I decided to run this on one worker, but you could run that on like 10 or 1,000 machines if you wanted to. Next thing is like the zone, like in which like cloud region do you want to run it. And the up to the true is basically I have that job running right now, but I want to update it so that you're gonna see like how that looked like. All right, so I have this now, like basically, probably most of you know Maven runs through and deploys my my job right now. So what we're going to see is like in the Dataflow console, we see all the jobs. And you see here, I did a little bit of try and error, I had some errors here. But it shows you all the jobs that are running. It shows you the streaming and the batch processing jobs. So you see here right now that we started our new job. It's running 9 seconds. It takes a little while. We basically have to provision the machines and install the SDK and set up a couple of things. So it takes a little bit to actually get started. And I have an error, of course. But okay, I'm not going to debug that live right now. But we have like still the streaming running, and I can show afterwards that it should run as well. So we have that running. And we're going to show a little bit of, like, yeah.
Okay. So just to summarize what we talked about when we built our pipeline just now, is we started with classic batch. And the amazing thing about all of this is we just had to add a few rules. We didn't have to change our algorithm much at all. So we started with batch. Then we went to batch with fixed windows. And then we started to build a streaming pipeline. So we looked at a basic streaming pipeline, and then we added to our pipeline to allow for speculative and late data. And then finally, we ended up with a pipeline of streaming data with accumulations. And we didn't have to change much about our code at all. We just had to add a few rules to do both batch and stream. So now we're going to go into a live demo that Robert just deployed. Just to summarize, again, this is how the demo works. So with every touch event, we send that to PubSub. Every click event, we keep track of whether it's a hit or a miss. And then in our Dataflow pipeline, we're windowing the data in 5-minute windows, as you saw, but we want to update the results every 10 seconds because we want this to be a real-time game so that you can see new results, see which team is in first as results come in. So we're sending that to PubSub, and then over WebSockets and the client, we're listening for updates for either a team or a player, and then we update the UI. And then we also send all the results to BigQuery so we can run some analysis on the top players later. And then in addition to the streaming pipeline, we also have a batch pipeline. So we read all our raw events from BigQuery, read them in Dataflow. In Dataflow, we just get the highest scoring players, and then we output the results to a different BigQuery table.
All right. So I want to show you, like, this is one of the main points, actually, if you talk about Dataflow. This is the thing that you can do batch and stream processing with the same SDK, with the same model. So you basically learn the system once, and you can do both of your big data tasks. So here I have a sample pipeline. So basically, like it looks pretty familiar. What I do here is I'm keying by team, I'm grouping, and then I'm calculating my team stats. This is the same classes that you have seen before. I'm not changing there anything. And then I'm reading, in this case, from a bounded data source. So I'm reading from BigQuery here because I need a bounded data source for a batch job. And then I'm writing my like aggregations back to BigQuery. So it's very simple to get, like, you basically can build up your data pipelines. You can start with a batch process, like you have like some batch data, you start building your pipelines, and then you can easily transform them into a streaming pipeline if you want to. All right.
So let's play a game. So it'd be awesome if all of you went to this URL, dataflow-colorsmash.firebaseapp.com, or you can use the QR code. And here's how the game works. So once you get to that page, you'll automatically be assigned a team color. And as the colors change, you score points for clicking on your team color. You can only click once per interval. And then we'll do some epic real-time data processing. So I'm actually going to open it up and play the game.
Yeah, me too.
I'm going to refresh the page. Here we go. I'm on team red, so I'm going to try to click all the red ones. Hopefully everyone's joining the game. You see that UID on the bottom, which will tell you why it's there later.
Oh, can we show the QR code again?
Oh, yes.
Yeah.
There's the QR code.
Oh, there's also a short link down there if you want to use the short link. So right now it takes a little bit. I actually found the bug and restarted the pipeline. So the pipeline starting down is about 2 minutes. And let me show you actually really quickly how that looks like. So we have here the pipeline running, as I want to show you this live demo. So we have here the pipeline running. It's elapsed time right now 2 minutes. So it shows you basically the pipeline that we have in Dataflow and Google Cloud Platform. We are reading from PubSub, we are sending the events to BigQuery, and then we are keying by team and by player. So let's see if we actually get some results here. It takes about 3 minutes to get to the point that it starts sending some elements. So let's give that a little bit of time.
All right, so let's switch back. In case anyone needs the URL again, dataflow-colorsmash.firebaseapp.com. And let's take a look at how it's doing there.
Yeah.
All right, cool. Okay. So it looks like here's the ranking. So red team is in first place right now. So it shows the hit rate for each team and your individual hit rate. So I've hit red 23% of my hits. So we can see that red is still in the lead. You can see it move around as different teams change. So while you're playing the game, we're going to go back to the slides. And I'm going to hand it over to Robert to talk about Apache Beam.
Yeah, so we talked, like, the title of this talk is basically an open model, right? And right now we have talked only about Dataflow and Google Cloud Platform and using the Dataflow service on Google Cloud Platform. But one thing, like what we actually did is we donated Dataflow to the Apache Software Foundation as an incubation project to actually commoditize it and basically give it to the open source community, which enables you to actually move your data pipelines from like your on-premise systems to any kind of cloud providers. So Apache Beam is basically the unified model that we have that we talked about, the 4 questions, when, where, what, and how, and it supports multiple runners as well. So it has multiple SDKs. Right now, the Java and the Python SDK is available. The Java is the most sophisticated, most full-fledged supported one, since this was the initial SDK that for Dataflow that was built. But Python is coming up as well, and we are looking basically for others to contribute other languages as well. So you have multiple SDKs to write your pipelines, and then you have multiple runners as well. One that we showed right now is the Dataflow runner. You can run it locally on your VM, on like your laptop, and you can also run it on other projects, for instance, Apache Flink and Apache Spark. We have runners there as well. So we are still in the process of growing the community around Apache Beam. Please try it out. It's on GitHub. Check it out, like what it is, how it works, and it basically enables you in the future to write your data processing pipeline in Apache Beam and also run them on Google Cloud Platform. So let's recapture like how this whole how did we get to Dataflow and what do we want to actually achieve with it. So if MapReduce undoubtedly kicked off a whole industry of processing large amounts of data, and Google developed and improved their data processing pretty much in a closed environment. So we had only a finite set of file formats, and we can basically improve and iterate much faster, basically, because we don't have to custom all of the things. So we brought out a couple of, many papers, but nothing that actually people could get their hands on. So we are really glad, actually, that these papers inspired the open source community to build the systems. And the open source community also went even further and innovated on themselves. So this is really great, and we encourage that a lot, and we also support a lot of these projects. So with Dataflow, basically what we want to bring together these worlds. We want to bring together the world which was developed within Google and the open source community. So we have basically also a different product on the Google Cloud Platform called Dataproc, where you can run your Apache Hadoop or Spark cluster. And with the Apache Beam model, we actually basically want to have the bridge of bridging the Google environment and the open source communities. All right, so you were playing a game, and I mentioned something about finding the top score in the game, top players. To do that, we're going to use BigQuery, which is where we were outputting some of the results in our pipeline. How many of you have used BigQuery before? Anyone in here? Looks like not too many of you. So a quick overview. BigQuery is our big data analytics warehouse tool. It's a managed service, and it scales really well. So you can query terabytes of data in seconds, and it's all written in familiar SQL. It scales, as I mentioned, from bytes to petabytes. And BigQuery has a REST API, so you can access it from many client libraries. If you're not familiar with SQL, BigQuery also integrates with many data visualization tools like Tableau. So you can easily create visualizations based on the data you're storing in BigQuery. You can instantly share your data sets. So you just need to add a user by email or an alias. So you can add a group to your data sets, and they can instantly have access to all of your data. And finally, everyone gets a free monthly quota. So you can query up to a terabyte of data for free every month. We've got a bunch of sample data sets. So if you want to learn more, I definitely recommend trying that out. But right now, we're actually going to do some live queries. So you can access BigQuery through the REST API. Another way to access BigQuery is through our web UI here. So you can visualize all of your data here and actually run the queries directly in the browser. So this is the table we're going to be looking at, and here we can see the schema for our table. We've got a timestamp column, a UID, a team, color, and a device. We're keeping track of whether you're playing on desktop or mobile.
I have a feeling most people here are playing on mobile. So this is what some of the data in our table looks like. And I've got some queries saved here that I want to run. So first I want to see, let me make this a little bit bigger, the hit percentage by device type. So I want to see if there's a bigger hit percentage whether you're playing on desktop versus mobile. So here we're just counting whenever the team equals the color. So whenever you have a hit, we count that as a hit. And then we divide the number of hits by the total, and we're ordering by hit percentage. So let's run that query. And we can see that on desktop, the hit percentage was actually quite a bit higher, 56%, compared to 49% on mobile. But we did have many more hits on mobile. So that is our device type query. Let's take a look at another one. So we can also see the hit percentage by team. I think the red team was in the lead last time we checked. This is the same as the other query, but instead of device, we are grouping by team. And we can see that red had the highest hit percentage, 56%, also had the most hits, and then followed by green, yellow, and blue. So the last query I want to run is I want to find out actually who the top players were. So who in this room had the biggest hit percentage. And as I mentioned before, you saw in the bottom of the game, you have a UID. We actually have some prizes, I believe. Do we have the prizes here?
Yeah. We will have the prizes at our
No, we
Google.
have prizes.
Oh, we have the prizes. Yeah, awesome.
Thank you,
Perfect.
Alexi. So we're going to give a prize to the top player for each team. So this query will tell us who those people were. And if it matches with your UID, you can come on down. So row 1, 2, 3, and where's blue? Oh, we don't have a blue. Not a lot. Oh, okay. Here's the blue one. So I'm gonna go back for a second. So if your UID matches any of the ones in the top 3 rows, come on down.
Take a picture and then compare.
Yeah, take a picture of the screen. I'll leave it up for a moment, and then I'll go to the next page. We didn't have a lot of blue team members, it seems. Okay, I'm gonna go to the blue one shortly.
Maybe we can copy them out and show.
Yeah. Anybody have a match yet?
Anybody match? Oh, we have one match. Awesome.
Come on down. We've got some prizes. I'll go back to the other screen. So again, these 3.
Which team?
Second match.
Which team are you on?
Which team?
Which team?
Yellow.
Awesome.
Okay,
All right.
we have another match. What team are you on?
Congratulations.
Blue. Okay.
Cool. Very nice.
We have yellow and blue. Any red or green team members?
Congratulations.
Which team are you on? Red. Awesome.
Perfect. Congratulations.
Thanks.
Were you on
And
the
what was
green?
missing?
Yellow?
Yellow again. We just had yellow.
The third from the top.
This one? This yellow?
All right. I should have compared the UIDs. 8, 9. Yes, you are. So the other yellow.
I don't know what.
You were which one?
The blue one. I'm the 8th one. I'm team red.
Oh, this one?
Oh no, just the first.
Just
Just the first 3. Yeah, the first one from each team.
All right. I guess we are out of our devices, so good enough.
All right. Thanks, everyone, for playing. Hope you had fun. You can continue playing if you'd like. I'm going to go back to the slides.
All right. So if you want to get started with, for instance, BigQuery, you can go to cloud.google.com/BigQuery and learn all about BigQuery. But we're here to talk about Apache Beam. So if you want to learn about Apache Beam, go to beam.incubator.apache.org or search just for Apache Beam, and you can learn all about the new one model for batch and stream processing. We also like to get your feedback of the session, how you liked it, what we can improve, what we should do better, better demos. Maybe you have some demo ideas. So please go to this short link or QR code and give us some feedback.
Thank you. That is all we got.
Any questions?